So let's define a matrix vector product. This is a way to multiply a matrix times a vector. So if A is an m by n matrix with columns a1 up to an, and x is a vector in Rn with entries x1 up to xn, we're going to define the product of A and x. We're going to notate it with just concatenation. We'll write it as ax, and it's defined to be the linear combination of the columns of A where we use the entries in the vector x as weights. So a few things to note here. The product is only defined if the number of columns of A equals the number of entries, the number of rows in X. So an m by n matrix, I can multiply it by a vector in Rn. So I'm viewing that as an n by 1 matrix. Another thing to note is the way the sizes work out. So if A is an m by n matrix and x is an Rn, so I can take the product Ax is going to be a vector in Rm. So let's go through an example. Suppose I want to compute this product. So by definition, I'm going to take the columns of A and the linear combination that arises from using the entries in the vector x as weights. So I'm using 1, minus 2, and 3 as the weights. And then I just compute using the definition of scalar multiplication and vector addition. Right? And so here I took a 2 by 3 matrix and I multiplied it by a 3 by 1 matrix. So notice the 3's match, and I end up with a 2 by 1 matrix, or a vector in R2. So we can express linear combinations as matrix vector products, which means that we can start talking about linear systems also as in terms of matrix vector products. So let's start with an example. The linear combination 2v1 plus minus 4v2 plus 7v3, I can view that as a matrix vector product where the matrix has columns v1, v2, and v3, and the vector has entries 2, minus 4, and 7. So notice I'm just taking the weights and creating this vector here. Right? And the vectors here tell me what vectors arise in the matrix. And so now we want to try to translate this into what it says about linear systems. Basically what it's going to tell us is that a linear system we can think of as a matrix equation. So let's see what that looks like. So let's take the linear system given here. If I express it as a vector equation, I get x1 times the vector 1, 0, plus x2 times the vector 2, negative 5, plus x3 times the vector minus 1, 3 is 4, 1. Right? And so if you notice, the left-hand side of the equation here is a linear combination of these columns. And so I can express this as this following matrix equation. Right? So I'm using the coefficient matrix of the linear system. I'll have a vector of that corresponds to the unknown, the variables, and then this vector b. And so we have this matrix equation ax equals b, where a is just the coefficient matrix of the linear system. Okay, so now we're going to talk about some properties of the matrix vector product. Basically, it's going to behave like a product, which is going to justify its name. Right? So for any matrix m by n, and any vectors u and v in Rn, and any scalar c, we're going to have the following things. Right? So first, matrix vector product is going to distribute over vector addition. Right, so A times U plus V is AU plus AV. Second, it's going to play well with scalar multiplication. So namely, if I take the matrix A and multiply it times C times U, I'm going to get the same thing out as if I multiply A times U and then scale it by this scalar C. Let's go through a proof of this. Right, so first, in order to prove these things, we're going to need to express everything in terms of what it said in the definition for the matrix vector product. And so I'm going to give names to the columns of A. So I'll write A as A1, A2 up to AN. The vector U is going to have entries U1 up to UN. And the vector V is going to have entries V1 up to Vn. And we just want to show that the left-hand side is equal to the right-hand side. And so we start computing. Right? So a common mistake that students often make is they'll start with the statement left-hand side equals the right-hand side and simplify, 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 and get something equals something, and they put a check mark. And that's just not a proof. Right? And so we're going to start with the left-hand side, and we're going to compute using the definition, and we're going to simplify and end up at the right-hand side. Okay, so the left-hand side is A times U plus V. And since I gave names to everything, it's just this as it's given here. Right, and now I'm going to use the definition of vector addition. So the vector U plus the vector V is just, I add each entry component-wise. And now I'm going to use the definition of matrix vector product. And I'm constructing the linear combination of the columns of A. Linear combination of the columns of A using the entries of U plus V as weights. And now I'm using the property that the scalar multiplication will distribute across the scalar addition. And now I'm using the fact that vector addition is commutative, so I can put all the entries involving the U's together and all the entries involving the V's together. And then this is just A times U plus A times V, which is the right-hand side as desired. Okay, and so you should try to prove statement 2 at home. If you get stuck, notice on page 39 of the textbook, Ley gives a proof, but he only proves it in the n equals 3 case. And so you should try to write out the general proof.